So, instrumenting software builds to detect stealth stuff and so on. Who am I? I do defensive IT security at a large German transportation and logistics company, and that's my day job. This talk is not about my day job, but it's kind of related. Linux detection engineering, the background plays a role. I've also considered myself a free and open source enthusiast for quite some time. I've been a developer, Debian developer for more than 20 years. So I know a bit or two about how all the messy software gets built and packaged into Linux distributions. So that will be playing a role. In my day job, I have been building observability tools in the past based on Linux Audit Subsystem. I've talked about that in a different talk, but we are moving toward a world where eBPF using eBPF for observability is a possibility even in the large enterprise. The old distributions are being faded out, and so we can actually get to use the good stuff. And sometimes when I listen to talks or conversations, something clicks in my mind. What I call bad ideas, and sometimes those bad ideas don't go away, and I start acting on them. So this is a story about something like that. One such talk was given at this year's FOSDEM. Tobias Specht talked about finding anomalies in a Debian packaging system to detect supply chain attacks. I'm not a big fan of the term supply chain attack because it doesn't really grasp what is going on. Industry outside the software industry knows about supply chains, but it's all about fixed products that are not changed afterwards. Software is not like that, but we all know that, right? So Tobias' idea was pretty good, and I'm kind of ripping it off. The basic idea is while software gets built, any kind of software artifact, you get to look at what the compiler and the compiler toolchain does. And you build what he calls a supply graph. The supply graph goes back from the finished artifacts to the source files via several stages, processes that have been involved. And then you go and look for anomalies in the supply graph. I've tried to do this from the bottom up. So let's take a look at the GNU Hello package. GNU Hello is a very useless package. Its main purpose is to showcase all the tools the GNU project has come up with to build portable software. AutoConf comes to mind, AutoMake. There's some stuff in there about localization. It's basically, its purpose is to show developers how to set up GNU-style projects. The tool is written in C, so the bit of text at the bottom of the slide shows what the finished program does. It just outputs "Hello World" and that's it. But that's not the point. If we know a bit about how a C compiler works, we assume something like this. The hello.c is read by the C compiler. The C compiler writes a temporary assembly file, which gets passed to the assembler. The assembler writes a hello.o, an object file that gets linked into the finished executable. So that's what we might think. It's not as easy as that. GNU Hello comes with a bunch of compatibility libraries or code that also gets compiled, and this is the full list. those files get compiled into object files also, and they then are linked to a static library. And that static library goes together with the hello.o into the hello executable. This is I've tried to visualize a bit what this looks like. Don't get caught up on the on the details, but you kind of get to see that this gets messy very fast. You cannot do with visualization really, but there's a graph structure there, and you can go. Theoretically, you could go back by hand from the finished product, the hello program, the executable, to all the source files, and figure out if something funky has been going on. So to go into a bit of details, what actually happens for every such .o file, .c.o file, there's a GCC call that's triggered by a makefile. The GCC executable runs a different program, CC1, in the case of GCC, which produces the assembly file that I mentioned. And for this, it has to read the hello.c and many header files, so it gets even more complicated. Many header files that are pre-processed, and then the assembly is generated, and then the assembler is run, and I think the assembler just gets to read the .s file and then produces the .o file, the object file. For all the other dependencies that are put in, or the other source files that are a part of the GNU Hello package, those are then after the object files have been created, we can observe the static linker or the archive tool. It is spawned, gets to read all the O files and writes the .a file. And so on. Finally, it gets all put together. The command lines are much longer than what I've shown here on the slides. If I had shown the whole command line, especially with hardening flags and everything and paths, you wouldn't be able to read anything. But so this is the gist of it. And assuming the source graph, assuming that we have no network activity during a regular build, which is the case for Debian's packages, they have to be able to be built in an offline environment. So all the build dependencies have to be there in the first place. We should be able to construct the source graph just by observing a few different operations. File open operations for reading and writing are pretty obvious. Maybe file rename operations, that depends very much on the compiler and other toolchain stuff being used, and sub-processor creation. That's it. So this is very much doable with simple eBPF probes, which means we get to do our observations with very little overhead. There are other alternatives that are not as good. Ideally, an implementation would not rely on inner workings of the compiler, how it works. Using LD preload might be possible. Might be a way to instrument a compiler toolchain that are linked dynamically, but this wouldn't work for statically built tools such as the Go compiler. Using strace is it kind of works if you don't care about performance overhead at all. So with what I'm doing in my day job anyway, or what I'm working on in my day job anyway, I thought I could just try eBPF probes. And this actually works. The source graph generator, it produces a JSON document from all the activity it has observed. It spawns the make or whatever you want to call as a child process, and then just observes which process gets to read which file and to write which file, and then it all falls together. Here we have to map processes to the files that they read and write, but that's basically it. That's enough to build our graph. And the most famous example that might have been detected if we had something in place back then was the XZ backdoor from last year. The backdoor worked just at a high level of view of the backdoor was that the attacker added an object file that had not that could not be observed to come out of a compiler or a linker. So in our graph it shows up as an anomaly, so to speak. You'd have to kind of write detection signatures for something like this. But this is very much feasible. The backdoor also patched some C source file that existed there, which is very unusual for a regular C-based tools that when they are built. I've also been able to pinpoint reproducibility bugs with tool chains that are not a simple C compiler. When the OCaml system, you can when you build OCaml programs, on most architectures you get to choose whether to build bytecode programs or native executables, and the OCaml compiler always produces two files, an interface file and the bytecode or native code file. And if you try to parallelize building both variants, the compiler instances may step on each other's toes, and this leads to interesting bugs with race conditions and such. So this is visible in the source graph as well. My code base at the moment, I have to apologize that I can't publish anything yet. I have plans to when I release the stuff that I'm doing for work, the Laurel Successor project. It will include a watcher tool to build to watch build processes, and it will also. I'm going to also provide scripts that or other kinds of signatures that that can be used on the source graph that is provided produced to find weird stuff. And there's also a plan to provide a CI integration. I've checked GitHub Actions should be possible to support, because you basically get VMs where loading BPF probes is possible. So that's a plan also. But no release today. I've got to do some cleaning up. So that's it for my talk. Thanks for attending, and then slides will be published later today. If you're interested in this stuff, come talk to me or contact me later.
Let's see if we have a few questions.
Thank you for the presentation. It's a long time I have not done development, but I remember that there was something called NM that was...
Can you speak up, please?
It's a long time since I have not done development, but I remember there was a tool called NM on Linux that was allowing to get the symbols out of library .o or an executable, and from there passing it to Grapher in Python or whatever to do this thing. What is the advantage of your method compared to, let's say, more artisanal way using NM?
Well, NM gets you the symbols, but it doesn't. It doesn't give you any information about what kind of stealthy weird stuff might have happened, might have been snuck into the package you're trying to build. There's another. There's another issue that. Oh, never mind. Sorry.
So, thank you. Cool talk. A quick question. Do you plan to add that to Debian reproducible builds?
Debian reproducible builds is absolutely useful, but it wouldn't have helped us with the XZ mess.
Yeah, I mean, like, add this as a layer to the concept of reproducible builds as an alarm layer or something like, yeah.
I'm absolutely open to that. I haven't talked to anybody from the reproducible builds org people.
Please do.
Yeah, okay. So this is still the early stages.
Thank you for your talk. I noticed the NM comment, but this tool could probably also detect backdoored compilers.
Possibly. It depends on how the backdoor of the compiler is implemented. It really depends. Yeah.
Did I see a hand? No? All right. Thanks, Hilko.